A forward proxy acts as a mandatory checkpoint. Organizations deploy them to audit and control all outbound traffic leaving their network. This architecture places a highly privileged node between the internal network and the public internet. An attacker aiming for internal systems relies on this exact piece of security infrastructure to grant them access. In May 2025, a security researcher submitted HackerOne Report 550766 to GitLab. The report detailed how a single unsanitized input field could cascade through an outbound proxy, mutate in transit, and ultimately force a back-end database to execute malicious code. The most dangerous vulnerabilities do not bypass security architecture. They use that architecture against itself. GitLab allows administrators to configure automated webhooks. If a webhook needs to authenticate with a third-party service, users can define custom HTTP headers for those outbound requests. The application layer failed to sanitize a specific set of invisible characters in these custom header input fields, carriage returns, and line feeds. The HTTP protocol uses a carriage return and line feed, /RN, as a structural marker forcing text onto a new line. By injecting these characters into the webhook field, an attacker silently breaks a single outgoing package into two distinct blocks. By leaving these two structural characters unfiltered, the application gave end users the ability to rewrite the raw formatting of the outbound network request. This image captures the attacker's first move in Burp Suite. They intercept the outbound webhook request and manually alter the custom header string. They start by injecting an artificial content length of 3 declaration. Immediately after, they inject a dummy string, the letter A and a colon, followed directly by a GET request targeting an internal Redis database. The injected CRLF sequence acts as a hard stop. It prematurely terminates the first set of HTTP headers. Everything following that sequence, the dummy string and the Redis request, is pushed down into the payload body of the original request. At the application layer, the GitLab server reads this entirely as one single valid outgoing webhook. It packages it up and transmits it. This payload operates with a dual nature. It is a valid sequence of bytes to the application sending it, but a malformed set of instructions to the network node reading it down the line. That outbound traffic leaves the GitLab server and hits the organization's Squid forward proxy. This diagram illustrates HTTP pipelining, allowing the proxy to process multiple requests over a single connection. Reading sequentially, it hits the attacker's double CRLF sequence and stops, routing the first portion towards its original destination. Because of the pipelining rule, it interprets the remaining payload as a new HTTP request, routing this envelope into the internal network. The proxy has unknowingly laundered the payload. It took external user input, repackaged it, and issued an internal request that inherits the proxy's own privileged access. The attacker's secondary target is an internal Redis database running on port 6379, visualized here rapidly processing commands. This is a blind server-side request forgery. The attacker can use the proxy to fire commands at the database, but they cannot see the resulting output. They also have to navigate the database's internal security. Modern Redis synthesis deploys strict cross-protocol scripting defenses. If the database receives an HTTP request containing standard keywords like post or host, it identifies an unauthorized protocol and immediately aborts the connection. The attacker bypassed this entirely. By carefully structuring the smuggled payload in the webhook, they ensured the resulting request omitted both the post and host keywords. With the connection open, the payload now has to speak the database's native language, the Redis Serialization Protocol, or RESP. The attacker traversed the network boundary, evaded the database's security tripwires, and established one-way communication with a critical backend service. The final objective is manipulating GitLab's internal file hook worker background process to execute a reverse shell. The attacker wraps their Python reverse shell inside a Redis eval script. The injection imposes strict constraints. Everything is lowercased and no spaces are allowed. The attacker substitutes spaces with the internal field separator Linux variable, keeping the command executable. Finally, they calculate the exact byte length of the script and prepend that integer to the payload. By solving for these constraints, an attacker turned a public text field into a remote execution terminal deep inside a protected internal server. This network topology map traces the full attack path. An injected webhook hits the proxy, splits into a new request, bypasses Redis security, and forces a worker to execute a shell. This behavior is often mistaken for a configuration error within the proxy. In reality, the Squid proxy was operating according to the documented HTTP pipelining standard. It was functioning exactly as it was designed to. This is a protocol collision. Two distinct interconnected systems parsed the exact same stream of bytes according to two entirely different sets of rules. When standard correct behaviors interact in unexpected ways, they create invisible vulnerabilities that no single system can detect on its own. GitLab engineers faced a severe operational dilemma when designing the patch for this issue. The production environment contained nearly 1.5 million existing encrypted webhook records. Executing a forced database migration to validate those legacy headers carried a high probability of causing breaking changes for enterprise customers. The implemented patch introduced strict input validation that fails only when entirely new headers are created or when existing headers are manually updated. Effective enterprise security patching requires a delicate negotiation between neutralizing a threat and maintaining the stability of a live system.